How are you doing this morning? Glad to hear it. Good to see you. A couple little course updates. So today, '17th. All right. So a couple things. Thanks for your patience on the project proposal. We will have time to get that up because what we want to do is have you all submit your ideas this week. Okay. Submit by Friday at 5 p.m. There will be an assignment on Canvas. For those who are in machine learning, it's a similar format. Basically, there will be questions on a form that you have to submit. And then Tuesday of next week, a week from today, so Tuesday, be Feb 24, be a project workshop, okay, in class. So you all should have been assigned to a group at this point, or TA got all the people who didn't have a group. They should be assigned to groups. If you're not assigned to a group, that's an oversight. Let's get you assigned, okay? Be a project workshop. You want to be here in class with your group. And we're going to discuss your project ideas. Our TAs will be there, DJ and Vivek. We're going to split up and talk to each of the groups about your project ideas and say, we'll see, this might be, you may be able to do. This one might be trickier, okay? It leads you in the right direction on a project, okay? All right, so your TAs you'll be in their hands for that day, okay? So project workshop, be here, because you're always here. I definitely count every single person here, okay, with your group. Okay. That's important because because a lot of people have tend to have cool ideas for what they want to do for your project. We just got to find a way to sort of constrain them down so they're doable within a single semester. We always advise start simple, and if it works, then you make it more complicated. Okay? All right. That's a project proposal. Now for the quiz, there's a quiz that's now been officially posted. There was some confusion because it got published and unpublished. That was a Canvas thing. They changed how quizzes work on us and created confusion, mostly on my part. Sorry about that. But it is now posted. Again, it's multiple choice. Open book, open note, okay? It's not timed, but it needs to be done by Thursday at 5 p.m., okay? That should all be in the okay? Just not open each other, okay? You can't ask each other for the answers. Just open book, open note. Really, it's just an open lecture. You can watch the lectures. You pull up my lectures, pull it up, it's fine. The idea is just you have to answer the question, right? A note, open book. Some of the basic concepts, all right? So, soon we should have your homework 2, which will be on optimization, which is what we've been covering for the last 2-ish weeks, okay? We cover things like linear and quadratic programming, and you're going to be applying those using MATLAB. That's what homework 2 will be like. As I'm sure some of you noticed, it's good to start early on the assignments because if you don't, you can run behind and not know how to debug things at the last minute. We only have so many office hours in a week, okay, to help you out. But I think a lot of people, I was impressed by what a lot of people were able to come up with for solutions. And I hope you all learned to check the homework FAQ page for looking for answers to common questions. We will update that as well for when homework 2 comes out. So, any questions before we get started for today? Okay. All right. I think today's the day where we have both optimal and control together. Is that a good time to review on control from this class's own perspective of what you need to know? A good amount of time on optimization now, how you set up some optimizations, how you set up your cost function, your constraints, and your decision vector, okay? set up those problems in the right way, they can be convex, or they might not be convex. Okay? All right? And we figured out how to take those optimizations, put them into solvers in MATLAB, and it spits out answers. We've done that in the last 2 coding lectures. Okay? So now we're going to put them together. All right? So today, specifically, we're going to get toward trajectory optimization. We're going to move in this direction. But I'll give you a basic overview of the types of control, just a review, okay? So, methods for combining optimization and control. Okay? There are 2 general types of control that we've talked about. There's feed-forward control. That's when you just send in a signal. It's just a signal. You're not using it, that doesn't change depending upon the feedback. Okay? It doesn't. So it's when you just turn on the oven. Okay? It's not sensing anything. Turn it on. Or if I know that I'm just going to do this motion, I'm just going to wave my arms like this. Okay? I've decided I'm going to wave my arms like that. Now, if someone comes over and slap my hand, I can then move it around to avoid it, artfully, deftly. Okay? And there's feedback control, where you use feedback from the sensors. And recall that they will often look like this. This is a feed-forward control. Here you have a controller. Here's a plant. Now, there's your output. Feedback, where you have a controller that takes in information from the output. Here's your controller. There's your plant. You feedback. And you compare where you want to be, right? So we used to call this open loop and closed loop control, right? Okay? Well, you can use optimization to help with either of these types of controllers. Short answer. Anytime you have a controller, anytime you have decisions to make, an optimization can do that for you. Okay? The classic manner, so of decisions you have to make with the control, are the gains in your feedback controller. Those little K's, or capital K's, I should. Right? Who chooses those? We do. Or we could have an optimization choose them for us, right? So one example, optimizing a feedback controller. Where if you have some states x of t, you've seen a number of times now, right? You might have some desired state. That's x desired, right? Your u of t, which is your control input, is equal to the minus k x desired minus x of t. Where this together, your desired minus your actual, what does that mean in terms of control? Error. Okay? And this, of course, these are your gains. And they can be in a matrix. That's an example that we have done, where we have created a matrix of a couple of gains and did a PD controller with them, right? We choose those, right? In those gains, and a classic example for that is an LQR controller. Linear quadratic regulator. LQR. Now, we've not done the LQR derivation in the class yet, okay? But the idea is that it's an optimization. You want to optimize those gains, so you have an optimization. What do you have to define to come up with to set up your optimization? What three things? Cost function, constraints, decision variables in your decision vector. Right, okay? Well, in LQR, your decision variables are your gains. Okay. Right? And your cost function, okay, call it J, is the integral from time 0, time infinity of x transpose of t q x of t plus, and I'll do it on the next line because I'm running out of room, u transpose of t r u of t dt. We've introduced this before, but the idea is that here's your state. Here's your state. These are basically multiplying them all together and adding them up. So it's like a bunch of squares of your states. So when you have a state that is not near 0, the cost adds up. And it gets integrated from time 0 to time infinity. Okay? So it means any time that your controller is away from a state that's 0, bad. A regulator is a controller that tries to drive your state to 0. Now, who defines what 0 is? You do. So you can make anything 0 theoretically. Okay? That's why it's called a regulator. This term here, what does that punish? What's the cost? What drives up your cost? Anything? This is the error. This is U of t. What's U of t? Control input. The more effort put in, the worse it is, right? There's your cost function for LQR. Constraints, it actually has no constraint. One of the weaknesses of LQR. So you might say, cool, we have a cost function. We have decision variables. We'll find some fancy way to put that into a MATLAB optimizer, and it'll tell us the gain K. Nay, my friends, nay. I can do better. Very smart people have figured out how to solve this by hand, such as Riccati, created the Riccati equation. Okay? All right? So where you can derive optimal K. Given A and B of an LTI system, one of the other major limitations of LQR has to be LTI. What does LTI stand for? I forgot. Linear time invariant. I didn't know that. Thank you. Of an LTI system. There's A and B matrices. Call the x dot equal to AX plus BU. Remember that? Getting rid of the of t's. Save my wrist. And Q and R. These things up here, right? Riccati equation. Okay. And there are multiple versions of the Riccati equation. That's actually not the subject of today's lecture. Okay. This is to show you the different ways that you can use optimization, in this case, We took our he basically takes the cost function, takes the derivative of it with respect to k, sets it equal to 0, meaning it'll be a local minima. Turns out it's the global minima. And you can solve for k. It's not easy to do by hand, but you can do it. Computers have a very fast way of solving them. It gives you your gain matrix k. All right? I'll show you an example of people using LQR, but not only LQR, to make something cool happen. Here we go. This is a video that came out when I was a grad student in 2011. This is a triple pendulum on a cart. Now, the full disclaimer. So what's happening here? There's a belt that's moving that bottom cart around, and it was balancing that triple pendulum. Okay, the fact that it swings up, that's something different. We'll get to that in a minute. LQR doesn't make it swing up, per se. But when it gets up to the top, all these new swinging pendulums there, that right there, it's LQR happening right now. What he did, Tobias Gluck, very nice guy. He responds to my emails. Very nice. Okay? They linearized that triple pendulum on a cart. We did linearization in class. Pretty nasty equations, but you can linearize them. You can use MATLAB to help you, just like we've done in class, right? That gives you your A and your B matrix, right? Well, you've got your A and your B matrix. Awesome. He makes the zero state that you want to be the pendulum at the top, linearized about that, and he has A and B. Then Q and R. Who chooses Q and R? We do. We do. The Q and R are matrices. Now we choose. And the bigger the Q values are, the more the controller is going to punish a bad state, the error. What if I make R really big? What's that going to punish? What's that? The effort, right. So if you make R really big, it's going to try to make the controller lazier. Okay? So you choose those Qs and Rs, and it changes the controller, right? It comes out of the optimization. But again, the Riccati equation allows you to do the optimization by hand. Or I should say, without iterating through different guesses, right? Does anyone remember when we were showing what the optimization was doing in class when we were coding it up? I turned on the iterations, and it'll start with a guess, and it'll try another guess, and another guess, and another guess. It iterates through. It's a bunch of computations. It doesn't have to do that there. Just use the Riccati equations. Okay. That's pretty cool, right? But the LQR, it's not doing the cool, jangly swing up. The Riccati equation in LQR is doing the feedback control, the balancing. Poke it a little bit, it'll try to balance it. That's one example. But to get the cool swing up, we can't. What's going to happen to the A and the B matrix for our LTI system? Are they still going to be good? What is the assumption when we're linearizing a system? Stay near that operating point. I'm telling you, friends. That's not near the operating point. That's about as far away as you can get. So you can't just pretend it's linear, right? That makes sense? That's okay. So what you have to, so what Tobias did and what people do in all kinds of dynamical systems that are very nonlinear is they come up with a plan for how they're going to swing it up. And that becomes a feed-forward controller. Okay? He has planned that, okay, if I need to swing this up from the bottom, I have to like shake it to the left like this, shake it to the right like this, and then go up. In your homework, you did this. I gave you the shakes, though. I gave you the forces to put on the cart and swung it up, right? Then you turn on your feedback controller, and then it balanced. Okay? By the way, that balancing controller, guess what I used to make it? Anyone guess? Smell, poo, R? LQR. Used LQR. I found an A matrix, found a B matrix, gave it a Q and an R. I chose the Q and an R, gave me a gain matrix, done. That's what you typed in for your homework 1. But for the feed forward, how to shake it and swing up, I used trajectory optimization. That's what we'll talk a little bit about today. So, another example, you can optimize a feed forward trajectory. Okay? Of inputs U of t. Okay? That's pretty cool. That's what, so what this does is doing all of the planning for how you swing it up from the bottom to the top. So let's do, and so the idea is that you would have some system. It could be linear, it could be LTI, or maybe not. But you define what you want that system to do with an optimization, which means you have to define what? Decision variables, cost function, constraints. Okay? Back to what Tobias did. I remember we were showing this off at conferences. I'm not showing off, I didn't do it, but we were all talking about it at conferences at the time. It was pretty cool that he did this. So he set some constraints. Constraint being, hey, the system is going to start down. All the pendulums are faced down. And it's going to end up. Those are constraints. That's what it must do. Okay. And for a cost, he said, let's use as little torque as we can. That way we're not making it shake too much. Not pretend we have too much torque. And as constraints, you can put limits on how much torque you can give to the motor going back and forth. Okay? Because we don't have infinite torque, infinite force, infinite strength. I do, but not everyone does. Okay? So, those would be the constraints for this problem. The cost, minimizing torque. So, it's got to get from the bottom to the top while minimizing torque. But what were the decision variables? Okay? The decision variables, as you saw in your homework, look something like this. So, look at our decision vector. Okay? Decision vector W. Okay? We can put in a lot of different control inputs. U1, U2, U3, that's a 3. Don't let your lying eyes deceive you. N. Transpose, so we make it a column. We're not monsters. Okay? And the idea is that these U of t, you might have some final time. On this axis, you might have time. And there's some final time, t final. And on this axis, you have U of t. And evenly distributed in time, you have points that I am drawing arbitrarily. Okay, I'm drawing at them at arbitrary heights, but they are all lined up with these different time points, okay? Okay. And the idea is that your function, U of t, your control input, is defined as just an interpolation, connection of these points. How high are those points? Well, that's here. That's U1. That's U2. That's U3. All the way up to UN. So the optimization says, hey, I might need a little bit more torque here, a little more input here to move up the pendulum, to swing it around right. Well, it'll slide it up. Oh, I need a little bit less here. slide it down. So all your decision variables, they define this little shape here. We call it a spline. It doesn't need to be a spline, but a spline is an extremely common way to define a trajectory. It's really easy. You just say, hey, at this time, I want that. At this time, I want that. Connect them with a line. Doesn't need to be a linear spline where these are lines. No. You have quadratic splines, cubic splines, quintic splines. Pick your spline. Question? The decision vector for an optimization, which we call W, consists of a bunch of variables, right? I'm just calling them U's. Okay. And what do they represent? They are representing U of t. This is just an extremely common way to define a trajectory. Not the only way. You could define, if you wanted, a polynomial. You could say, I want my U of t to be equal to U of t to be equal to some polynomial a0 t plus a1 t squared, and then these could be your decision, right? Either way, what's important is you have to define U of t as variables in the decision vector. Okay? For our feedback controller, our variables in the decision vector were the gains k. Individual real values that we can change. Here, we're making them splines. Did that answer your question, Cricket? Kind of, sort of? What did I miss? It's nothing? Okay, I trust you. All right. So the key, we must define a function U of t, which is continuous. With a discrete set of decision variables. And your homework, I gave you U1, U2, U3, U4. And then you did this, and you put that into your simulation, right? Okay. But if we define our control input like this, and we make this our decision vector, guess what? We're setting up an optimization problem. One that we can give to a solver in MATLAB or some other programming language to solve. That's what I did. Get you this little curve, right? That's what I did. I did the work for you. Next time, guess who's doing it? All right. That's your decision vector, right? Okay. You can also have constraints. Okay. You can have what are called path constraints. Those can be constraints on your x of t. You could say, hey, at no point when I am moving this cart around, excuse me, sir, I don't want my cart to go past this far to the left or this far to the right. That's a constraint on the path. It's not allowed to go that far, right? That's an example. That means you would take one of the states, which is the cart position, say, I don't want it to go past those positions. That's a path constraint. Okay. You can also add terminal constraints. That's constraints on your state at your final time, TF. Clearly, we have terminal constraints on this optimization problem, right? Pendulum's got to end up at the top. Got to do it. If you don't do it, you failed. Bad job optimization. Okay? You can also have boundary constraints, which are more general, meaning that you could have constraints on x0, x at time 0, combined or not combined with the final time. We do boundary constraints all the time in walking robotics. Okay? So for instance, if I want to come up with some really efficient way to walk, I will set up a boundary constraint where I say, guess what? The initial state of my robot, that could be chosen by the optimization. I might not know what it needs to be. I could be mid-step, choose all my speeds, all my angles, all my velocities and such here. But then after 2 steps, I got to be right back where I started. I'm not telling it exactly what I need to start at. I could be like this or like that. Could be up to the optimization. As long as I end up like this after 2 steps, the same thing, it's fine. Okay? But the boundaries at the beginning of end of time for your state are the same. Does that make sense? Okay. And similarly, friends, cool. You can also have control input limits. Okay, that's on U of t. It can be lesser than or equal to some minimum or maximum. U max, U min, you put bounds. And if you have and specifically in control, we call this when you're limited at how much you can put out for your control input, we call this saturation. Saturation. At some point, you just can't push any harder. Saturation. Good. And there's all kinds of clever constraints that you can also add. This is not completely exhaustive, but typically they can fall into one of these categories, right? Those would be your constraints. Okay? Now for your costs, anything's on the table, friend. Okay? It can be anything, but common costs will be you can have an effort cost, which is U of t squared dt from 0 to your final time, integrated. So you want to, over the course of your entire trajectory, minimize cost. Okay. Here's a common one. No cost. 0. When you're doing a trajectory optimization, if it's not working, one thing we'll say is like, hey, try making your cost 0 and just see if the optimization can figure out how to do anything within your constraints. Okay. Because these optimizations will often be nonlinear. When you have a nonlinear constraint, when you have nonlinear programs, nonlinear optimizations, you no longer have that beautiful guarantees of convex optimization where like, oh, it'll find it right away. It might. The optimization might find a solution, and we'll show you really good ways to help you find it, but the guarantees are probably gone. So one trick we'll do is say, hey, try running the problem with no cost, see if we can figure it out. Okay. Effort cost, no cost. You're going to have an error cost. And to be clear, these little squared terms, they are, of course, assuming a single state. If you want to write them more generally for these squared terms, you might do something like x of t transpose x of t. That will take all your states, square them, add them together. It's basically a norm. Norm squared. Okay? So, but it's really up to you. You get to choose what the cost is. These are some common ones. Another one you can do is minimize time. So you can minimize trajectory time. Yeah. What do I mean? What do I mean by that? Well, this TF here, the final time of the trajectory, we've been assuming it's constant. At least I have been in my head. Maybe I didn't say it out loud. And that could be some amount of time I give it. I get 5 seconds to figure out how to swing up the pendulums. Okay? But what's stopping me from making that a decision variable? Nothing. I can make that a decision variable, and all of a sudden, watch out, I'm going to do something crazy with this. Let's see if this works at all. All of a sudden, if it can change the total time in the trajectory, well, it'll shrink down the amount of time or expand the amount of time. It kind of works. See what I'm getting at? If it can change the final time to be smaller, it'll squish together the times, so it does that. Or stretch them out like that. Okay, all right. Enough of that. So if you want to minimize time, your cost function would just be, the thing we want to minimize, right? So Tobias, with this pendulum, I want this one. Again. My entire YouTube feed is pendulum stuff. Can't imagine why. All right. So he could say, hey, I want to know the fastest possible way to swing up this pendulum within the limits of my actuator, right? Okay. Make sense? You're finding your decision vector, finding your cost and your constraints for a problem. Let's do an example ourselves on paper. Because once you define these things right, you can set up a trajectory optimization and run it. I see 2 questions. In the back, yes. No question? You were just stretching? Okay, yes, take cricket. Can you have multiple cost functions? If you add them together, you can. Then you have one cost function. Question is, if you give it 2 cost functions, which one is it minimizing? Which one's more important, right? And for all the tools we use in class, it doesn't know. You have to give it one optimization. Now, there's an entire field called multi-objective optimization, and that's about multiple cost functions, right? And that there can be sometimes principled ways to handle multiple cost functions, right? The easy way is you got 2 things you care about, add them together. And you multiply one by a big number and the other one by a smaller number. You weight them as linear combinations. Okay? But are you starting to see how a lot of this class is just defining what do I want? Once you define what you want, there's a lot of tools out there that'll give it to you. Make sure you ask the right thing. Okay? So, but very importantly, look at some of these constraints here. X of, okay, it's saying, okay, we have a constraint that's depending upon the final state at some future time. Well, in class, we get that by simulating, right? To know what that final state is. When we're simulating the cancer growth models, we don't know the final state at the beginning. We know the state at the beginning, not the state at the end. Only once we simulate it, we know, right? So that means that for our constraints or our costs, we're going to be running computer simulations. Okay? And if the optimizer is trying different things, oh, I'm going to try this, how did that work? I want to try this, how did that work? It could be running tens, hundreds, thousands, sometimes tens of thousands of simulations, trying different things to see what happens, right? So these optimizations are less likely to take milliseconds. They might take seconds, minutes. Taking hours, call your doctor. Guess I'm that doctor. Okay. All right. So let's do an example. Sorry, that's the second of types of ways to use optimizations with control. Okay. Really quickly. The third general category. I mean, there's sort of feedback and there's feed forward, right? Another way is to actually run an optimization that is so fast that it runs inside of the feedback loop. So you define what you want. Instead of this being a controller like minus kx, where you've already defined what k is, you say inside of here is an optimization, an argument. Okay? And we'll do some examples of that. Okay? So see here, last example is optimization in the feedback loop. Okay, so the idea is that here your controller is some optimization. You're trying to minimize something and find the inputs that minimize something. Goes into a plant. Then there's some feedback here. Then when something changes, like your current position or the current state, it changes the optimization, comes with a new control input, U of t, and it goes into the plant. Those are cool. We do them all the time. I'll show some examples real quick. See? Like this guy. This is a drone. See the drone? Gonna zip around those pendulums. Look at that. That's doing a trajectory optimization so fast. Here we go. Go again. Hopefully, we can see it real fast. TJ, you did this. Oh, he's gone. The guy who did this experiment just left the room. Okay. It is running a trajectory optimization to get to the end, to the other side of this. And it's running it so fast that when the pendulum changes, it changes the trajectory optimization, reruns it again, comes up with a new plan over and over again. It's called model predictive control. Another example. Pull it out here. Here is our digit robot down the hall in the other room. Let's see here. It's running two types of optimization in the control loop, okay? It is doing a model predictive control type controller where it is planning where to go, which is just basically, do I want to move left, right, forward, backward? That's the general plan. But for controlling the entire body, it's running what we call an operational space controller, which is saying, hey, I want to make my center of mass move in this direction. And then it solves a quadratic program that we coded up in class on Thursday, and such that it comes up with all the torques and all the joints that'll move the body in that direction. Okay? It actually all simplifies down to linear constraints and a quadratic cost. It's quite cool. Anyway, so that way when he's pushing it around, that's my student Tienza. He's now working at a humanoid robotics company in China, employing this exact stuff right now and cutting edge stuff. And yeah, so it's just solving a quadratic program about 1,000 times a second, figuring out what the torques on the robot need to be. Okay, so when it gets a change to its state, because he's pushing it with a piece of paper, I guess. All right, the optimization changes, it reruns, comes with a new solution over and over again. That's optimization in the loop. Pretty neat, right? So the examples would be, oh yeah, this is the thing that he was showing. Where'd it go? Where'd it go? I like that part there. Randomly, he decides, I'm going to make the robot's center of mass want to go higher or lower. Okay, he's like, oh, up, down, up, down, up, down. So it changes. All we changed was the cost on the fly. We just changed the cost. So, hey, we want our position to be a different position. The cost changes, and it drives it up and down. Pretty neat. It gets tall. It actually gets very intimidating when it gets tall. All right. Okay. So, in examples are things like called model predictive control. or MPC. That one's cool because you can set up a trajectory optimization problem. If your dynamics are LTI, which we all know what it stands for, right? And your cost is linear or quadratic, then you can make your trajectory optimization a quadratic program, which means it runs really fast. You can just do it over and over again, okay? Another one's called operational space control. We will do operational space control. We'll do both of these. We'll do model predictive control. We'll do operational space control. We'll write them both from scratch in class. Not something as complicated as that robot. We'll do something much simpler. They're both really cool, in my opinion. That's why I teach this class. I think it's neat. So let's go back to trajectory optimization. Let's do a trajectory optimization example. Okay? We want to write the optimization problem. To drag race a car. Okay. Optimization problem, we're going to need our decision variables, costs, and constraints. Okay. So I'm going to drive a really cool car. Watch this. Look at that mass. Drag race, for those who know, in this context, means starting from a dead stop and then stopping, going across the finish line and coming to a stop. I don't know. I'm not a racing car expert. Is it technically in the rules that you have to stop, or is it just preferable so you don't die? Just beneficial to come to a stop? Okay, in this case, we're going to require it to come to a stop. Okay, that's my rules for drag racing. Okay, all right. It's going to be on ground, which I also think is in the rules of drag racing. Okay, and we want it to start here, and we want it to end over here. Okay. All right. And we have a control input, U of t, which is a force on that car. We're going to define its position, some displacement S of t for that car. Okay? I'm going to drag race this car. Okay? So I want to know, so drag race the car. Specifically, we want to minimize, it's a race, we want to go fast, right? So we want to minimize the time to reach and stop at S final. Here's this right here. This would be the rate. That's S final. That position right there. Okay. Okay. Now we are also. This is a realistic car. We are subject to acceleration limits. Okay. We are subject to limits on U of t, where U min less than or equal to U of t less than or equal to U max. Okay? We're going to write this optimization problem. It means decision variables, cost constraints. 5 minutes left? Okay. Plenty of time. And we forgot to record any of this stuff, I'm realizing. It's okay. Streaming well, so don't have to worry about it. How to practice. That career fair. You all have careers now? Good. Okay. Oh, no, we don't all have careers. Let's fix that. Okay. With optimal control. Cost function, minimum time to career, plus maximum cash, multiple objectives for cricket. Okay. Not that we all want cash, but to be clear. But all right. subject to limits on control input. So we need decision variables. We need a decision vector. Okay? W. Okay? And I'm going to define a bunch of points in time where I define my control input U. It's a force. I could have called it F, but it's Tuesday. U1, U2, U3, up through UN. Who decides what N is? We'll decide what UN, what N is, how many points we have. So where, oh, and we're gonna need I made a boo-boo. Move to the side. I'm also going to add as decision variable the final time when the simulation ends. Because I'm going to want to minimize that. Where you're going to have t and u of t. You're going to have all of these points defined in even spacing. They don't have to be even spacing. It's just your life is easier if they're evenly spaced. So this is TF. These are connected by linear splines. Do they need to be connected by linear splines? No. But it's easier if they're linear splines. For each of these things is U1, U2, U3, up through UN. Okay? That's our decision vector. Okay? That's going to define our U of t, which is important because we're going to have to simulate this car, drag racing car. Is there a word for that? Car? Okay. So let's do the cost next. Let's make our lives easy. Your cost function. Okay. We've called it f of w in the past. The only problem is we're soon going to have dynamics, so we're going to have multiple little f's. So we're going to call it j. And it's dependent upon our decision vector. And what are we trying to minimize, friends? Time. Really easy cost function, right? But the challenge comes in the constraints. Okay. So let's assume. Okay. Let's start at. I'm going to scroll up. I'm going to write into the problem here that s of 0 is equal to 0, and s dot of 0 is equal to 0, meaning starting at rest at the start, right? Okay. Our constraints are going to be, so we want to stop at the finish, meaning that s at time tf equal to 0, and it has to stop. So the velocity s dot tf at time tf also equals 0, right? But in order to get this, we have to have our simulation tell us if we start or stop. So if we're going to simulate, guess what we're back into? Back into state space. We got to write out our dynamics of our car. Okay? So what I'm going to do is I'm going to write our dynamics. So our dynamics, we need to know what our states are. Well, let's write out our general, so it's going to be mass times acceleration, s double dot, equal to the sum of the forces on your car, which is u of t. Oh, it's super. Question. Well, you first. STS, oh, sorry. I have a really easy solution to that problem. What's the solution to that problem? Don't move. I would have coded this up and I would have gotten don't move. I'm like, what did I do? Thank you. That's number one. Thank you. Applause for people paying attention. I was testing you all. Pass. Okay. Yes. Sorry at the stop of the finish. SF. Okay. That's just F equals MA, right? We're not assuming any friction on here. Okay. Now, we need to know what our state vector is. Now, per our procedures for state vectors, we count up the lowest and highest order derivatives of these things. And you might say, hey, S double dot is the highest and lowest derivatives of S. But, my friends, no S. So we're going to need to have S in the computation here, right? So for states, for S of t, the highest order, second derivative, lowest order, 0. U of t, highest is, this is our control input. Spoilers here, it's going to be lowest order is 0, highest order is 0. The number of states, 2. Our decision, sorry, not decision vector, our state vector, we'll call it x of t, is going to be s of t and s dot of t. If we were to write this in state space form, okay, x dot of t is going to be some function of x of t and u of t. U of t is already defined. So x dot of t, s dot of t, s double dot of t. On the right side, we want to write it in terms of states and inputs. Well, S dot is a state. Right there, I see it. I spy state. S dot of t. And S double dot of t is defined up there. U. Mathematicians will tell you that you can divide both sides by m. S double dot of t equal to 1 over m u of t. So this is just going to be 1 over m u of t. Okay? Really simple system. Basically, you just have to take your control input and integrate it twice in order to get your position, right? So there's a special name we call for this system called the double integrator. Because we integrated twice. We're really good at naming. Okay? So if someone says, oh, we use a double integrator model, it's like, oh, yes, of course. Something you integrate twice, and they, obviously. All right. Or you could call it a drag race car and sound a millimeter cooler. Okay? All right. So we got that. Those are aerodynamics. We've written them out. So that means we need, we need to figure out what the S, your position at time final is, whether or not it's equal to SF. Okay? So when we're writing up our constraints, we have to write up a simulation using these dynamics. Okay? And we'll use things like ODE 4.5. Just like we did for the simulation part. We're going to have a simulation inside of our optimization. Okay? So we will integrate these dynamics to solve for S of TF and S dot of TF. We will use, so that's what you have to do, okay? And we're going to use things like ODE 4.5 for that in class on Thursday. Okay? So what's going to happen is that this optimization has been told, here's your decision variables. It's a bunch of U values and a little TF value. To them, it's just, to the optimizer, it's just numbers, you know, that you're going to give it. Okay? Then what you're going to do is you're going to say, okay, excellent. Here's your cost function. It's just the last value of that decision vector, TF. Okay. Seems pretty easy to minimize to me. Okay. And you say, nay. Nay. You have this constraint, which will be a function that you just give it. And you say, okay, you gave the optimizer, just give me your decision vector, and I'll spit back out these two constraints as equality constraints. And I'll tell you how far off you are. Okay? It has no idea what's happening in that function. It just gives you U's and a final time. You tell it, is that true or not? If so, how far off, right? Just like you gave it constraints in the linear and quadratic programming section, we gave it A and B matrices here, there. Now we're going to give it a function, okay? And inside of that function, we're going to simulate the car moving. It's going to go, it's going to miss. All right? And what it's going to do, the optimization is going to say, okay, if I move around these a little bit, these values will make this one a little bit bigger, 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 this one a little bit bigger. What happens when I try each of those combinations? Does it get better or worse? Better or worse, better or worse. And if it gets better, it moves it, it makes it bigger. If it gets worse, it makes it smaller. But in order to know if it got better or worse, it's going to check the cost function, and it's going to check the constraints, which means every time it wants to check, it's going to run that function. And that function is doing what? Running a simulation. Those little time points. It won't make the noise. I'll make the noise. Keeps doing it over and over again. Keeps trying things. You can see it's going to run a ton and ton of simulations, right? See if it gets better and better and better. Now, my friends, I'm missing one constraint. What constraint am I missing? Missing at least one constraint. Missing one constraint. That one. We got to put that in there as well. That you, for U1 through all UN, all of them have to be less than some max and greater than some min, right? You can only brake so fast. You can only accelerate so fast. Why do I like this problem? Well, that's personal. But one thing that's cool about it is I know the answer already. I know if the optimization got it right. So I know if we made a mistake or not. Something's going wrong. Let's assume. Sorry, here. Sorry, we'll try this again. I apologize. Let's assume that this is our plot over time. This here is U min. This is U max. This is U of t. Anyone know the shape I should get? It's going to get me to the end as fast as possible and come to a stop. I've seen some hand gestures. I'll fill in the, well, anyone drag raced before in this context? No, okay. you're alive. I guess the answer is by nature didn't. You stomp on the gas, I think. No expert. Maximum force. Then when you have to stop, if we assume that U max and U min are the same, which they aren't in real life, minimum force. So you come to a stop. That should be the answer it finds. We code it up for Thursday. Any questions about that? Now, to be clear, this will be defined by points, right? So if we have a finite number of points, what it will look like is zit, 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 and there'll be a little bit of a diagonal when it gets to the next time point, right? The best that it can do. That approximates that. Does that make sense? We should get that answer. When you're trying new coding problems, start with things you know the answer to. That way you know if it's wrong when you have to debug something. Okay? So that's the answer. So in fact, we'll say, hey, bang on, bang off. So this solution has got a name. It's called bang bang. Classic answer. We're going to try to get the bang bang. Thursday, right? Simple problem we know the answer to. But the same principle applies if you're doing this pendulum thing, right? You're trying to figure out how to swing up this pendulum. In fact, exactly what Tobias did. He did a trajectory optimization. Figure out, I want to start there, I want to go up there. That created a little U of t for him to jingle the cart around, okay? He had to add a couple extra little gimmicks, like one thing he did is that not only did he linearize pendulum at the top to come up with an LQR feedback control, he linearized the dynamics at different points along the trajectory. And each of those points come up with an A and a B matrix, and therefore came up with a gain matrix K, and would switch between them along the trajectories in case there was little errors in how he was shaking up the pendulum. Pretty cool, right? So a really interesting combination of both trajectory optimization and optimal feedback control, LQR. So that's what we're going to do on Thursday. We're going to write that trajectory optimization. But I do want to sort of give you a little preview as to where this is going to move in the future, okay? Because this approach that we'll take on Thursday, it has a name where anytime that we want to check if a constraint is right, we have to run a simulation, right? We have to know if it got to the end to know how well it did. The optimization has to check, right? The idea, so this approach where we need to know over time, where did our state go? Okay, we start at state here and it goes, well, somewhere, right? And that process was a time marching simulation. Right? Starts at the first time, steps forward, steps forward, step forward. You can use Euler's method, or you could use ODE45 or any number of methods, but the point is it steps forward in time, right? This approach is called single shooting. I'm not trying to use gun metaphors. This is just the name of it, okay? All right? The idea that you start at your first state, run a computer simulation, see it ends at the last state. Check to see how it did. So simple. Why would you do anything else? I mean, that's the first thing I tried. I didn't know it was called trajectory optimization. I was like, I have an optimizer. I have a simulation. I wanted to do the thing. Put the simulation in the optimizer, see what happens. I didn't even know it was called single shooting. That's what it's called. But there are weaknesses. The fact that it has to keep running, it has to run so many different simulations, right? there a way around that, though? There is. Pretty crazy, but we'll see. We're getting to that. I mean, but another thing that's a challenge is that, let's say that your first guess as to what this is, you have no idea how to shake that pendulum to make it go up. Your first your first guess might not get anywhere near it. In fact, probably won't, right? It's possible that your cost function to the optimization might look like this, where here's your cost function, we'll call it J of W, and that's not time. Oh my gosh. Might look like this. It's got all kinds of weird local minima, and those local minima are nowhere near solving the constraints. The optimization will go there and it's like, I'm stuck, I don't know what to do. I don't know how to get it up, to move it to the top. And so do I have to come up with a better guess? Well, one thing that we've found is that instead of doing a single shot that goes all the way to our final time, T final, what if instead you only took a little shot for a little time? Okay. Now, for a nonlinear dynamical system, if you run it for just a tiny, tiny period of time, it starts to look linear, doesn't it? Local linearity, remember that from school? Right? Which means the integration of these dynamics, this constraint, this integration of the dynamics constraint, which is a pain in the tush, because it's nonlinear, does look more linear. Easier to solve. Starts to look a little bit more like a quadratic program or a linear program, if it isn't linear, even if it isn't precisely one. Okay. Okay. Doesn't get me all the way to the end, but fine. What if then I add another decision variable? In fact, I'll make it blue. So that's another decision. Okay. Right now, our decision variables are just control inputs, right? And the final time. Things we want to know. How hard to push when and how hard, right? But I'm going to add another decision variable. Sorry, this is state here. Yep. That's state. Another decision variable for my states at that time point. And then I'm going to simulate for a little bit of time again. Again, the evolution from there to there is basically linear dynamics. This is a smaller shot, right? Much more linear, right? Then I'm going to add another decision variable. I'm just putting them in arbitrary places, shoot for a little bit of time, right? All these tiny, tiny little shots, until eventually you get to the last, which is T final. T final, okay? Now, this makes no sense because your state is teleporting in a continuous system. That's not good. But what if I added a constraint that said, hey, guess what? The end of this simulation must line up with that state. I added decision variables for state along the trajectory. And I added more constraints. This seems psychotic. Seems like more things the optimizer would be trying to fix. But because what would otherwise be nonlinear dynamics are much more linear, solve. Counterintuitively. It even might run faster, even though there's a lot more decisions to make. Okay? This is called multiple shooting. And it's way better when you have systems that are unstable or hard to find solutions for. Okay? Weird. Gets weirder. Okay? We're over time by a minute. The last one, we have no simulation whatsoever. Okay? In fact, we draw an imaginary line of where we want the system to go. and then check at points in the middle to see if they match our dynamics. And that's called direct collocation. That's a wild one. That's what Tobias used to do trajectory optimization for this highly unstable nonlinear system. That's it. See you Thursday. Get the quiz done by 5 p.m. Open book, open note. Multiple choice.